Okay, I guess then we are done with the break and we return to part 2, where we'll have again starting a little bit with a lecture and then coming to the work that you should actually do. And probably we are not going to finish this, but you can then do this as a homework over this. I don't know whether you are off probably. I mean, there's an exercise that you can do. Homework is always voluntary. Yeah. I'll open with this slide saying that everything that we now programmed you can easily do with the reduce function, where you is all in one line. Yeah. Where we just put everything. Do we want to do this as a small starter, or do we skip this and go to the next? Okay, you know how to do. Maybe I go here. Okay, maybe you know, and we'll do this later in the exercise. So now we try to do it a little bit more advanced. So you noticed we had this, we talked about this loop scheduling, and everything that we did here was, of course, static loop scheduling, and where every process was finite, was knowing when to end, because we simply had a static amount of work to do, and when the work was done, they all terminated. In practice, we often have the work depending on the result of what we are doing. And this is in particular the case when we use adaptivity. So for example, you want to know pi within a specific precision. So what we did now is we had no idea about this. We just say, okay, we use a very, very many points to do this integral, and then what comes out is what we take. Okay? But suppose you want to have it with a given tolerance. Then the simplest thing you could do is to start calculating it with a low number of intervals, increasing the number of intervals, and compare how much it changes. And as long as you're not satisfied with this change, you're increasing the number of intervals. So I have to warn you, from a numerical point of view, this is a very, very, very poor approach, doing it this way. Especially just so doing it this way is a very poor algorithm in a sense, but it has everything we need in order to look at it from the point of view of parallel programming. I don't want to go in depth into numerics. So just what we do is we start with k equal to 1. Then we do the integral. We increase the integral. We increase k, compute another integral, compare the two, and see whether they are larger than a tolerance, and if so, we go on, and once we have where the difference between two of these are smaller than a given tolerance, we say now this is our result. And this is what we want to implement. Now, problem being, of course, we have to communicate all of this. To a master, so it doesn't matter now whether we use master and slave, or we use reduce or divide and conquer. But then the master, the emperor, so process 0, has to communicate to everybody that we are going on calculating. Yeah, because we have not yet finished. And the question is whether we can do this efficiently. Now, if we do it in a naive way, the following happens. Yeah? So the slave will do their work, then the slave is done working, so then the masters are combining results and see, yeah, okay, we have to work again, so they call their slaves again. And they start working again. And what's the way we would call everybody we have to work on is by a broadcast, bcast. Now, what will happen if, for example, in this version A, which is a blocking version of bcast, is suppose you have several works that you could do. You have work part number 1 and work part number 2. Because everybody is in here, right? So you do your work that is depending on something and work is not depending on anything, then you do the broadcast. So what does the broadcast do? Broadcast is blocking. Rank 0, say rank 0 is the one who receives, who's sending out the broadcast, and all the others are receiving the broadcast. But broadcast is blocking, so rank 1 would only go, rank 0 would only go on working once everybody has received the broadcast. So if here on the horizontal line we have the time, yeah, so rank 1 is blocked here from when it sends until everybody received. So everybody called broadcast. If some rank calls broadcast before, so if one of the receiving ranks calls broadcast before the broadcast was sent out, it will be blocked, and it will be blocked until the last one called broadcast. So you see, there is a lot of time wasted. Therefore, it is sometimes useful to split your work into a part that you can do before receiving the broadcast and a part that is after receiving the that is somehow depending on the broadcast. So do the communication. So the first one would do the communication as last as possible, and the other thing is do the communication as early as possible, right? So if you do it as early as possible, will this be better? Not necessarily. For example, if there is one rank that has to do a lot of work before it can call broadcast, then the other ones are blocked very early, yeah, and wait here for a very long time before they can do the rest of their work. So both communicating as early as possible and communicating as late as possible may take a lot of time, because during this communication, during the broadcast, there is no work can be done. The only one who can do work is the one who has not yet called broadcast, or the other communication calls. So this is where these non-blocking operations become very useful. So non-blocking operations, of course, we have also the usual send operations, but here we'll now use broadcast, for example, for this example. So this is the immediate return. So we have e-send, yeah, and we have e-broadcast and e-others. So what e-broadcast does, it immediately returns, and it can, and then you can do the work. Then you can go on. You can immediately go on working, but there is, of course, a problem that if there is work that requires the data of the broadcast, so especially if you are on the receiving part, yeah, you cannot do the work that you may not be able to do the work that depends on this new data. So what you then can do is to introduce a wait. So there's a place where from here on I need the data. Here I have to wait. But the good thing is that this broadcast now is not blocking for the others. Yeah, so the others can go on working, and so in the end we usually end up working faster. So this down here, this is called called communication hiding. That you send off some work, send off some data, and do some work while the data is processed by the network. Yeah, and if you do this in an optimal fashion, so communication and calculation runs in parallel, then communication doesn't cost you anything. In an ideal case. Yeah, this of course also means that you have to do more calculations than you need to have communication, obviously, otherwise it wouldn't work. Okay, so this is a bit the things that we are wanting to use, and I'm talking about this now. Anybody here last year? Probably not. With the homework that we gave out last year, we saw that using wait statements is apparently a problem because most of your colleagues from last year did this wrong. So I guess I'll have to be a little bit stringent on this thing here. Okay, we'll try to understand the waiting. So this example here doesn't make a lot of sense, but it's just for the way it works. So the wait statement has, of course, to know what it is waiting for. Otherwise, it doesn't make any sense. Yeah. So you always have to know what you are waiting for. Therefore, MPI introduces something that is called a request. And this request, MPI request, which we call here now request, so this is a handle to the function call we are waiting for. Now you see this non-blocking. I should have written here non-blocking. The non-blocking send, e-send, so which immediately returns, sending a message 1, 2, 3, whatever, of integer length 1, yeah, and it is sending them to process to the process with rank 1. So this would be rank 0, sends to rank 1. This is tag is 0, com world, and so this is the one thing that is not in the usual sense. There is the request. So this is now the handle. Now we can do some work. So when we send, and this has not yet received, we can already start doing some work. Yeah, and once there is something where we have to make sure that now it has received, then before this we should wait. And now we wait for this function here to terminate, or not to terminate, sorry, to have been processed. So now we need to know which one has been processed, and therefore we need this handle request. Yeah, so we have to give this request to the wait function, and then we do something else. Yeah, for example, and the other rank is doing the receiving. So here's where we wait. So why is this important with this request, or what is a common error that we have observed? Say you're sending two things, which will often happen. For example, you do the thing in a loop. Yeah, you do the sending in a loop, as we have seen. Yeah, and now you do this with immediate return, and now you always put here request. So now what we are waiting for after doing stuff, waiting for the request. So will it wait for everybody? It will wait for the last one. Yeah? So now the problem is if the last one returns, but what we are actually waiting for was somebody else, yeah? Or we wanted to wait for all of them, yeah? For example, then we have just overwritten the request. So this in particular is a mistake that many of your colleagues did in their homework. The thing is, if you are just waiting for the last one, it often works. Yeah? So if you can be lucky, you're waiting for the last one, and if you have a favorite ordering of your operations, then this should usually work. And in particular, if you do communication hiding, and the work you are doing takes longer than the communication, it often works even without waiting at all. Yeah, because the thing is, if something depends on that something else has happened, and you do enough work in between, yeah, that usually it takes so much time, this work, that the operation of sending is finished, then usually your program runs very fine without waiting for anything. The problem is this is still wrong, because this is unpredictable. Yeah? And for a program being unpredictable is even worse than to be wrong. Because when it's wrong, then usually you can easily see that it's wrong. Yeah? But if it's unpredictable, then it runs 1,000 times. You believe it is a cool thing, you deploy it is with the customer, yeah, and it is very, very deep in a big project. It always runs, and then suddenly there is a network fault, takes a little bit longer, and everything crashes, and you have no idea why. Right? So this is, even though in your homework, yeah, so I mean the thing is of course the following. You do your homework, you see it runs, you present it to us, and think everything is okay, because it always runs. And it does, it always runs, but it's still wrong, because it is a coincidence that it runs. Yeah? You have not taken care of the possibility that a process has not yet finished. Okay, so now I'm talking a lot about how to do it wrong. The way you do it right is, of course, to get a request for all of them. Yeah, so all of them need to have an individual request. Like, for example, you put the requests in an array. Now, if you put the request in an array, then in C++, then in a C array, then of course you need to know the number of requests at compile time. Yeah, because the array length needs to be known at compile time in C. Fortunately, which is now not on the slide, but you can easily look this up, this also can be done with C++ standard library vectors. Yeah, because the C++ standard library vector is stored like an array. So if you have a pointer to the first argument, the pointer to the first element, yeah, of the vector, it can be used as with an array. Just you need to call a function to get the number of the size of the vector. So this wait all, the function wait all will wait for all of them, for all, or not for all of them, for the number of requests. Yeah, so you give the number of requests, and here you give the array, and together with, you know, the number of, so it will take, so basically you give the length of the array, yeah, but it will interpret the length of the array with this number. So for example, if your array, so what you could do, what you actually could do, if you have a big array with, say, 1,000 requests, but you only want to wait for the first 20, yeah, so what you could do is you hand the array and say you want the number of requests is only 20. So this will take the first 20. Yeah? So you're not lucky if you want to use, you know, you cannot skip over some of them. Right? Yeah, so one thing that is interesting in comparison to Lego wait, yes. So for example, right, so here it is written a little bit different. So the nomenclature is a tiny little bit different because the request here is just a request. It's only one request, so and this takes a pointer to a request. This is why we need the address operator to the request. While an array in C is already a pointer. Yeah, because it's already a pointer, here you don't use the address operator. Yeah? So maybe you want to write this down. This is a useful and a common mistake probably also in the exam. Okay, and here it has the request and the status, and this is the number of things. So now there are a few different wait statements, two of which we have now seen. There is the usual wait, which takes an MPI request or a pointer to an MPI request and a pointer to an MPI status. So this simply takes you so this is of course blocking. So if there's non-blocking operation, and this will now block until the communication is done. So wait all will wait for all requests, for all functions that have been called and are in this list of arrays. It will wait until all of them has returned. Not the returned is not the right way. Have been processed. And there are two more, namely MPI weight any. So MPI weight any will also take a list of requests, and this will return, or it will stop blocking, it will return, stop blocking, if any out of this list has been processed, and it will put the index of the one that won the race with returning first. This will put the index into this, or the rank of this into this index. And then there is a strange candidate that works a little bit, where I myself have a little bit problems understanding exactly how this is working, is for wait for some. Waiting for some is like waiting for any, but it will also accept that several of them returned at the same time, and now it will give you the number. It will give you the number of the ones who have been processed at the same time into out count, and also gives an array of their indices. Now this is a little bit strange, because this requires several processes to be done at the same time, where in reality they will not come exactly at the same time. So there is, a small interval, obviously, before it returns, and if they are roughly returning at the same time, you get here several out of them. So this is a little bit a strange guy, which will not be on the test, say, but it exists. Okay, so this is one possibility. You do the non-blocking functions. You do your work, and then when you are done with the work, you can do without the result of the non-blocking functions. You do the wait, and then wait blocks, and then if you once run into this wait, and then you wait until it has returned. So you're not able to do anything. You recover from this. Therefore, for this, if you just want to query whether the function has been processed, you can use test instead. So testing instead. So testing is like a non-blocking wait, if you will. It's a little bit strange, but because wait is, of course, always blocking, this is why they didn't call it non-blocking wait. But it's the same kind of function. Now, what does it do? It will, of course, immediately return, but it will write into the flag. So, okay, you get a request, you get a flag and a status. So you have one more argument, pointer to a flag. And it will write into a flag. If it's not complete, then the flag will be 0. And if it's complete, then it will be something different from 0. So the idea putting something, this is a little bit strange, because probably in a different programming language, this would be a Boolean, true or false. In C++, 0 is false, and everything other than 0 is true, right? So you have to think like this, and it is in an integer, so you can actually you can actually ask for an integer if flag, yeah? So this will be executed if the integer is not 0. Okay, but you can also write it in a different way. So for example, I find this a bit confusing, therefore I put it here with equal signs, yeah? So, but you can, so for example, you could, okay, or as a question. So if you, okay, I've not checked this, but I think you can just not flag would be the same as flag is equal to 0, right? Yeah, should be. Okay, testing a request. Sorry, the code probably doesn't make a lot of sense, but anyway, yeah, so we are this is the same example as before, we have this message 1, 2, 3, and we have the request, then we do a non-blocking send, we may do some work, and now we need a flag and use a while function. So now we do a test and we'll stay in this while loop as long as this here has not been completed. Yeah? So what you can do is you can do a test, you can test it, and now you can do something else that is not related to this message, and once the thing has been sent, you get out of this loop. Okay, so all the functions that you have for wait, you also have for tests. Yeah? So there's test all, there's test any, and there's test some. And they just work the same way. Yeah, right. So okay. So there's the only slight difference here is that test sum doesn't need an extra flag, yeah, because it has this out count. So this is the number of requests that have been finished, and if 0 have finished, then simply outcome is 0. So for example, if you have wait, in the wait sum, the out count has to be 1, yeah, because it waits for sum to finish, so it cannot be 0. But in this case, for the testing, it can be 0. Okay, now we are right. So now we are coming to the end of this brief lecture, number 2 for today, and now you are supposed to do the exercise, and the exercise here is to do this tolerance check and send with MPI casts that you want to proceed, yeah, do the so right, so you do this tolerance check. So this is, sorry, when I go back, right, so this function here should be implemented. So you do everything. Maybe I'll go briefly to the back to the code that we had. By the way, is this the one offset my rank? Main adaptive. I'm not sure whether I've the right or the wrong file. Main and so which was the one? I believe I'll just, okay, I believe I just saved it. Integral master offset. All right, right. So, okay, so I just gave it a different name, so not in order not to overwrite the other one, right? But this should be the thing that you've just programmed. And in this, there's already a little bit of preparation for us, namely this 4 int rounds. Yeah, rounds is equal to 0, rounds is smaller repetition, round plus plus. Now we started with repetitions. Repetitions is equal to 1. Now the idea is you can use this loop, yeah, repeating the operation as long until you are satisfied with last time's result. Okay, so this is number 1. I'm kind of in the wrong space here, right? Right, so let me go on. So this would be assignment 1 if we are able to do this, and after you have done this, we would like you to do it with non-blocking operation and with wait in order to try communication hiding. Okay, so these are the 2 things now you are supposed to do, and what I'm doing is I'm stopping the recording, and then we get started. So how do I actually get out of this again? I'm in the wrong spot.